Delayed until 2016 by sanctions and politics, the S-300 PMU-2 was studied against by Israel before delivery. Joint exercises with Greece in 2015 gave Israeli planners detailed exposure to the S-300 PMU-1 predecessor, enabling development of the Icebreaker electronic warfare missile and Harop loitering munitions designed specifically against S-300 radar vulnerabilities. In October 2024, Israeli strikes degraded the S-300 batteries protecting Isfahan, the most significant air defense suppression on Iranian soil since the revolution. The adversary had studied the system for longer than Iran had operated it. When the strikes came, that asymmetry was visible in the results. Presented as Tehran's domestic answer to the S-300, comparable range, indigenous supply chain, sanctions-proof, the Qaher-313's claimed 300-kilometer engagement range rests entirely on Iranian official disclosures, with no external combat confirmation. In October 2024, while S-300 batteries were struck in Isfahan, no Qaher-313 engagement was publicly documented against the Israeli strike package. The system, designed to prove Iranian air defense autonomy, has yet to demonstrate in confirmed operational use that claimed capability and confirmed capability are the same figure. Russia supplied Iran with 29 Tor-M1 short-range air defense systems from 2007 onward. In Iranian service, the Tor-M1 faced two compounding problems. Spare parts dried up after 2012, and integration with Iran's Chinese and indigenous platforms required workarounds that degraded the coordinated engagement capability the system was designed for. On January 8, 2020, a Tor-M1 battery shot down Ukraine International Airlines Flight 752 over Tehran, killing all 176 people aboard. The integration failure the engineering community had identified as theoretical killed passengers on a scheduled civilian flight. The problem was not theoretical. Modified from the Shahab-3 with Iranian guidance improvements, the Ghadr was Iran's primary medium-range ballistic missile through the 2010s, used in quantity during the April and October 2024 attacks on Israel. Arrow 3, David Sling, and USSM-3 interceptors achieved interception rates above 90% against Ghadr salvos in both engagements. The missile, developed to hold Israeli targets at risk, demonstrated instead the cost of fielding a medium-range ballistic against an adversary that spent a decade building a layered defense designed specifically to intercept it. Iran fired the missiles it had. Israel intercepted the missiles it had prepared for. Claimed capable of striking targets within 10 meters at ranges beyond 700 kilometers, the Zulfikar-Basir is Iran's stated precision ballistic missile. Operational firings in the April 2024 attack on Israel produced impact patterns inconsistent with sub-10-meter CEP. Targets within defended areas were not struck with the consistency that single-digit precision predicts. Post-strike imagery documented the distribution. The Zulfikar-Basir causes real damage at operational range. The precision figure in official statements is not supported by where the craters actually appear in the imagery that each employment leaves behind. Backbone of Iran's tactical ballistic missile arsenal since the early 2000s, the Fateh-110 has been used operationally in Syria, Iraq, and the April 2024 strike on Israel. Iranian officials attach CEP claims suggesting consistent accuracy within meters at operational ranges. Post-strike imagery from multiple firings showed impact distributions around but not on intended targets, at rates inconsistent with single-digit meter precision. The Fateh-110 causes genuine damage. The precision narrative in official statements is not supported by where the craters actually appear in the imagery that follows each employment. Unveiled in 2013 as a domestically designed stealth fighter, the IAIO Qaher-313 drew immediate scrutiny. Cockpit too small for standard instruments, intakes too narrow for supersonic airflow, canopy too shallow for a pilot in flight gear. The aircraft did appear airborne in photographs, though analysts disputed altitude and whether the prototype was jet-powered or carried a substitute power plant. Iranian officials maintained the stealth fighter claim. Aviation engineers maintained the aerodynamic objections. After 12 years, neither confirmed performance data nor a production count has been independently verified. The comment sections have been consistent. So have the analysts. Expertly identified as an F-5 with a modernized cockpit, the HESA Kowsar was unveiled in 2018 as Iran's first fourth-generation fighter. The fourth-generation designation refers to avionics, not to the maneuver performance, radar cross-section, or thrust-to-weight ratio that define the classification in Western taxonomy. The glass cockpit is new. The aerodynamic envelope, structural limits, and engine performance remain those of an F-5 that entered US service in the 1960s. The generation gap between what Iran calls it and what it can do in contested airspace is structural, not a matter of classification language. Reverse-engineered from the F-5E, the HESA Azarach is powered by a domestic engine assessed as lower thrust than the General Electric J85 it replaced. Lower thrust means reduced ceiling, lower top speed, and less payload to range than the original F-5E provides. The Azarach proves Iran can manufacture a jet combat aircraft under comprehensive sanctions, a real industrial capability that did not previously exist. It does not prove the manufactured result equals the aircraft it was derived from. The achievement is genuine. The performance gap relative to the original F-5E is also genuine. Distinguishable by a twin-tail empennage resembling the F/A-18 Hornet, the HESA Saeqeh was described by Iranian officials as a new design and by Western analysts as an F-5 with a different tail. Both are accurate. The production count is assessed at 6 to 10 airframes. What the Saeqeh proves is that Iranian engineers can study a tail configuration, fabricate it, and attach it to an existing airframe. What it does not prove is the aerodynamic integration, flight control adaptation, and structural analysis that makes a different tail a meaningfully different aircraft in contested airspace. Iranian-backed forces operated the Pantsir S-1 in Syria and Libya, where Turkish Bayraktar TB2 drones repeatedly destroyed Pantsir batteries, while their engagement radars searched for faster threats. The reaction time problem against low-speed targets in cluttered electromagnetic environments was documented across multiple theaters over several years. Iranian planners had access to proxy operation data showing exactly how the Pantsir failed against cheap drones, the same category of threat Iran itself produces and exports at scale. The organizational changes that data required were not made. The failure mode was documented before it was repeated. In June 2019, Iran's third Khordad medium-range surface-to-air system shot down a US RQ-4 Global Hawk at high altitude over the Strait of Hormuz. The most credible Iranian air defense success in years and a genuine demonstration of domestic radar and missile integration. The system's architectural problem is survivability. A known, mapped, fixed installation in a country whose air defenses have been studied by multiple adversaries for decades. The third Khordad demonstrated it could kill a drone on a clear day in peacetime. What it has not demonstrated is how it survives the suppression campaign that follows making itself known. Derived from the North Korean BM-25 Musudan with Iranian guidance modifications, the Khorramshahr is Iran's longest-range liquid-fueled ballistic missile. The same engineering property that gives it range creates its principal vulnerability. Liquid fuel requires a preparation window between fueling and launch, during which the system is stationary, above ground, and locatable by surveillance. Under sustained precision strike by an adversary with persistent ISR coverage, that preparation window is the engagement opportunity. The fuel that gives the Khorramshahr its reach requires time to load. Time is the resource a liquid-fueled missile cannot protect. Announced in June 2023 as a hypersonic missile capable of maneuvering at Mach 13 and penetrating any existing air defense, the Fateh-1's claimed terminal maneuver envelope was assessed by Western analysts as inconsistent with the observable aerodynamics of the displayed vehicle. The performance figures have not been independently verified through instrumented test data available in open sources. Iran has invested real engineering resources in the program. Whether the investment has produced the performance claimed in the announcement is a question the Fateh-1 has not yet been required to answer against a prepared adversary under real conditions. Designed for anti-ship targeting in the Persian Gulf, the Hormuz short-range ballistic missile uses a depressed trajectory to compress engagement timelines against ship-based defenses. The fundamental problem is terminal guidance. A ship moves between launch and impact, and maintaining a mid-course targeting update requires radar or drone relay under active electronic warfare. Iran's demonstrated ability to sustain that data link in a contested electromagnetic environment against a maneuvering warship with active countermeasures has not been confirmed in operational use. The Hormuz solves the trajectory problem. The guidance problem in a real naval engagement remains open. Without hostile action, without sea state, at a berth in Bandar Abbas in July 2024, the IRIS Sahand, a Moudge-class frigate, capsized and sank at its mooring. The Iranian Navy raised, repaired, and recommissioned it. The failure that allowed a warship to capsize in harbour was not publicly explained, and no root cause finding was published. Recommissioning without a public failure analysis means the fleet operating the recommissioned ship does not know whether the problem was stability design, maintenance practice, or loading error. The ship was refloated. The question that sank it was not answered. Originally built in the United States in the 1960s, the Bayandor-class corvettes entered Iranian service before the revolution and remained in active frontline inventory for over 50 years. Through the revolution, the Iran-Iraq War, the Tanker War, and 4 decades of sanctions. No engineering failure produced that longevity. Sanctions and budget constraints produced it. The failure is that a Navy operating 1960s corvettes as frontline combatants in the 2020s had 50 years to replace them, and, for reasons the sanctions environment makes understandable, did not. The engineering did not fail, the procurement strategy did. Iran's Moudge-class frigates represent the Islamic Republic's most ambitious domestic naval engineering program. 1,500-ton multi-mission surface combatants, designed and built under comprehensive sanctions, carrying anti-ship missiles, surface-to-air missiles, and torpedoes. The engineering achievement is real. Building a frigate without access to Western components requires solutions in radar, propulsion, and weapons integration that Iran solved domestically. What the class has not solved is the sensor and engagement range gap relative to the frigates of regional competitors equipped with Western systems. Iran built the hull it could build. The capability ceiling reflects the components it could not obtain. Converted from an Aframax crude oil tanker into a forward base ship, the IRIS Makran was commissioned in 2021 as Iran's expeditionary naval platform, projecting presence beyond the Persian Gulf and supporting helicopter and special operations at extended range. The conversion produced a large, slow, radar-conspicuous vessel with no meaningful defensive armament relative to its size. A forward base ship that cannot defend itself depends entirely on the air and surface assets protecting it, assets Iran's navy does not consistently possess in the threat environments where the Makran would operate. The capability it represents is real. The survivability calculus is not resolved. First shown publicly in 2009, the HESA Shafaq Advanced Jet Trainer has spent 16 years in a cycle of development, limited production, and uncertain operational status. The design is real. A domestically engineered two-seat jet appropriate for advanced pilot training. The Shafaq has not entered series manufacture in quantities that would justify the tooling and design program investment. Iran has a trainer design. Iran does not have a trainer fleet. Designing an aircraft requires engineers. Manufacturing it at operational scale requires an industrial base. In Iran's case, those are different organizations with different output rates. Basic jet trainer for the Islamic Republic of Iran Air Force. The HESA Yasin converts student pilots from piston to jet-powered flight before transition to combat types. The reported fleet size appears insufficient to graduate pilots at the rate an Air Force of Iran's scale requires to offset attrition across its aging combat fleet. A fighter force with an undersized training pipeline loses pilots faster than it replaces them. The Yasin solves the problem of having a domestic jet trainer in principle. It has not yet solved it at the scale an operational Air Force requires in practice. Built by reverse engineering the Bell AH-1JC Cobra, Iran received approximately 200 under the Shah. The Panha Tufan traces its rotor system, transmission and fuselage architecture to a 1960s design. Iranian engineers rebuilt what they could no longer import and produced a domestic attack helicopter that flies and carries weapons. The tactical question is whether structural engineering finalized 60 years ago provides adequate survivability and performance margins against the infrared missiles, radar-directed guns, and electronic countermeasures developed in the 5 decades since the AH-1J was a current design. The Tufan is a real helicopter. Its threat envelope dates to the Johnson administration. Described as operational in reconnaissance and light attack roles, the HESA Shahed-285 armed scout helicopter has no documented combat performance in any confirmed operational engagement. A helicopter designed for forward reconnaissance in contested airspace requires demonstrated survivability, sensor reliability, and weapons integration that can only be validated under real conditions against real threats. The Shahed-285 completes Iran's rotary wing indigenization program on paper and in official ceremony. Whether its flight performance and weapons integration deliver what the role requires in practice is a question engineering documentation cannot answer, and operational use has not yet been asked to resolve. Domestic long-range surveillance radars, including the Matla-ol-Fajr family, were positioned as Iran's anti-stealth detection systems, low-frequency designs intended to track targets that conventional microwave radars cannot resolve. The concept is valid. Low-frequency energy reflects off stealth geometries that absorb higher frequencies. The intrinsic problem has been documented since the first SEAD campaigns of the 1980s. A radar that transmits can be located and engaged by anti-radiation missiles that home on its own emissions. The radar that can see stealth aircraft announces its own position to everything hunting it. Visibility works in both directions. China's HQ-9B was positioned as the outer layer of Iran's air defense network. The system designed to stop high-performance aircraft and cruise missiles before they reached critical targets. The engineering failure of Iran's air defense architecture is not any single system, but the integration between them. A hybrid network of Chinese, Russian, and indigenous platforms that was designed and procured separately, speaks different data protocols, and requires manual coordination under the electronic attack conditions that would accompany any serious strike campaign. Each layer performs on its own terms. What Iran has not demonstrated is a network that performs as a coordinated system under live jamming and anti-radiation pressure simultaneously. Developed with Chinese design assistance from the Yuan-class diesel-electric program, the Fateh-class displaces approximately 600 tons submerged, well below the conventional attack submarines of regional competitors. The capability ceiling reflects the negotiation that produced it. Iran received enough of the Yuan program to build a submarine, and not enough to build a fully capable one. The gap between the Yuan and the Fateh is precisely the gap China decided to maintain when it determined what to transfer. Iran built the submarine that technology transfer permitted. The limiting factor was not Iranian engineering, it was Chinese policy. Every system in this list shares a structural condition, designed or acquired for a threat environment that has since been studied, mapped, and prepared against by adversaries with longer planning horizons and deeper pockets. The Tor M1 was integrated into a network it couldn't coordinate with under pressure. The S-300 was delivered after its countermeasures were already in service. The ballistic missiles fired in 2024 were intercepted at rates that reflected a decade of Israeli and American investment in exactly that capability. Iran built and bought the best it could under the constraints it operated within. The constraints were the problem. They still are.